Hello, welcome to Maths with EJD. In this video, I'll be talking about generating functions, and this is the introduction to that. Many other videos are coming after this, and it is still in line with the ideas of sequences and series. So this is going to be a standalone playlist, but then it will be added to the sequences and series playlist also. Come along, let's see how this looks like. Okay, so generating functions are powerful mathematical tools that transform sequences. They transform sequences into algebraic expressions, into algebraic expressions. Okay. They serve, they serve as a bridge between discrete structures and continuous analysis, enabling solutions to problems in fields like combinatorics, probability, and number theory. Okay, so welcome to generating functions. Next, let's talk about the definition of generating functions. Okay, so a generating function is a formal power series. It's a formal power series in which the coefficients encode a sequence of numbers. The coefficients encode a sequence of numbers. So for a sequence, for a sequence an, all right, for a sequence an starting from n equals 0 to infinity, its generating function, its generating function is, check this out, g of x equals a naught plus a1x plus a2x squared plus a3x cubed, and so on and so forth. And all of that can be summed in, can be summation from n equals 0 to infinity of an, all right, x raised to power n, basically. So that is what the generating function of a sequence an would look like. So it basically talks about the coefficient. I think there's an emphasis on the coefficients. So the a generating function is a formal power series in which the coefficients encode a sequence of numbers. Okay, so the focus is on the coefficients. Now, this formalism allows us to encapsulate an infinite sequence, into a single expression, enabling algebraic manipulation, enabling algebraic manipulation. So, having said that, let's talk about types of generating functions. Types of generating functions. Okay, first of all, we have what you can call the ordinary generating functions. Ordinary generating functions. Okay, that's OGF. Yeah, OGFs actually encode sequences using summation from n equals 0 to infinity an x raised power n. That's the type we saw the other time. A very good example of this example. So the sequence, okay, let me take that down. The sequence 1, 1, 1, and so on and so forth actually has the generating function. That's a generating function, which is g of x equals 1 plus x squared plus x cubed, and so on and so forth. So you can see that the coefficients in this situation are all 1, just like you see 1, 1, 1 all the way, right? So this is 1 over 1 minus x. Okay. That's if you take the sum to infinity for that, you have 1 over 1 minus x. And this is only true for absolute value of x less than 1, meaning that x lies between -1 and 1 in that situation. Okay. So that is about ordinary generating functions. Then we also have exponential generating functions. Exponential generating functions. Okay. Now in this case, yeah, those are EGFs now, right? That will be EGFs. So EGFs encode sequences, with summation from n equals 0 to infinity an x raised power n, now divided by n factorial. So it's more like ordinary generating functions divided by n factorial. Okay. So in that case, the example, you have example like this. You have this kind of example that the sequence 1, 1, 1, and all that has the exponential generating function, which is gx equals summation from n equals 0 to infinity x raised to power n over n factorial, and that ends up like e raised to power x. And that is the same thing as e raised to power x. Okay. So, I mean, in this case, right, if you start from 0, you have 1. If you go 1, you have x. If you go 2, you have x squared over 2 factorial and so on and so forth. So at the end of the day, it's more like, so it's e raised to power x in short in that situation. So let's talk about other variants of generating functions, other variants. So talking about other variants, right? First, we can talk about the Dirichlet. We have the Dirichlet generating functions. These are used in number theory. Used in number theory. Then you have multivariate generating functions. Multivariate generating functions. Multivariate generating functions used in combinatorics. Combinatorics should be something like the science of counting or something close to that. All right, so having said all of this, let's look at real-world applications. Some real-world applications of generating functions. Real-world applications. So we mentioned some of them already, but let's still go ahead. First of all, I've been talking about combinatorics a lot. Combinatorics. That has to do with counting problems, like finding the number of ways to partition a number or distribute objects. Often this rely on generating functions. Okay. Yeah, let me just go ahead and write that. So combinatorics are counting problems, right? Counting problems. So these are counting problems, like finding the number of ways to partition a number, to partition a number or distribute objects. Or distribute objects. These often rely on generating functions. So an example of that, the generating function for the number of ways to sum to n using integers from 1 to 3 is this: g of x equals 1 over 1 minus x into 1 minus x squared into 1 minus x cubed, like that. Okay. Now we also have another application in probability. So another application is in probability. So probability, in fact, I'm sure the first time I came across generating functions, it must have been under probability. So here, generating functions, model distributions. The model distributions, and then the ordinary generating function of a probability sequence, which you can call small pn, is a probability generating function, is a probability generating function which you can call, that's a PGF, right? And it is used to analyze random variables, Okay. Then number three, we also have this application in number theory. So here, Euler's generating function, Euler's generating function for partition numbers, that P of n is given by this. So you have P of n equals product from k equals 1 to infinity of 1 over 1 minus x raised to power k. All right. So we also have some examples, uh let me just say simple examples or general examples. Okay, let me just say simple examples, right? Simple examples of generating functions, though I've been talking about different examples all along. So I've talked about this. Imagine the sequence 1, comma 1, comma 1, and so on and so forth. And the generating function is 1 plus x squared plus x cubed, and so on and so forth. And the sum to infinity of this, of course, is 1 over 1 minus x. And that only holds for absolute value of x less than 1. Then you have another one, Fibonacci numbers. That's a very popular sequence. Fibonacci numbers. Oh, okay. Um, this is supposed to be sum of geometric series. So this is sum of a geometric series. Okay, sum of a geometric series. Then here we have Fibonacci numbers. So here, the sequence looks something like this. Starting from 0 and 1, then every other thing you get is the sum of the first two: 0 plus 1, 1, 1 plus 1, 2, 2, 1 plus 2, 3, 2 plus 3, 5, 5 plus 3, 8, and so on and so forth. So the generating function associated with that is just g of x equal to x all over 1 minus x squared. Okay. Then in conclusion, right? Conclusion, Generating functions, generating functions provide a versatile framework, a versatile framework to solve problems, to solve problems involving sequences. Okay. Then they simplify computations. They simplify computations. They reveal patterns. They reveal patterns. And connect discrete and continuous mathematical realms. Discrete and continuous mathematical realms. Okay, so that's all for this video. This is just the starting video of generating functions. So there's more to come. So be sure to subscribe to the channel and hit the notification bell. Also comment, let me know how helpful these videos are for you. And if you want me to teach a topic or solve a problem, then like and share so that more people can have access to this great content. Till I come your way again, have a great time. Bye.